One. Okay, recording in progress. Good. So you memorized all of your trig derivatives. I know it was like on a video one day, then I wasn't here, but you know all 6 trig derivatives, right? So when we quiz tomorrow, I'm going to throw some of those on there. Okay. Let's go ahead and evaluate this. Derivative with respect to x of cotangent cubed, that's what we say, of 5x squared plus 2x minus 1. This is a composite function, yes? So for composite functions, we have to use what rule? Chain rule. Yeah. And so rewriting it could be critical to identifying the layers, because the number of layers we have in the original function is how many links in the chain we're going to have, if you want to think of each factor as a link. So the outer layer is going to be what? It's the one most people miss. The cubed. The cubed. We're cubing the whole thing. So let me write this in layers. The outermost layer is cubed, okay? And then the next layer is cotangent. And then the next layer, the innermost layer, is 5x squared plus 2x minus 1, okay? So that's how we write it. Purple layer, red layer, green layer. Super important, right? Identify, rewrite, add parentheses, look before you leap, right? You don't want to like be in midair cannonballing and you look down and you're like, crap, there's no water in the pool, right? Now we can proceed to peel this onion, mixed analogies, right? From the outside in, or unpack these Russian nesting dolls, whatever you want to call it. So we have blob cubed, right? Blob cubed is the outer layer. So when I take the derivative, the d dx goes away. So it's going to be 3 blobs squared. 3 blobs squared. That's the power rule, right? 3 blobs squared. And what goes inside? Well, everything else, because we only do one layer at a time. Times, that's the other link in the chain now, times the red layer. What is the derivative of cotangent of blob? This is where you have to memorize it. What kind of cosecant? Negative cosecant squared, right? Tangent is secant squared. So cotangent is negative cosecant squared, right? Remember, all you got to do is put the negative and then the cos in front. So negative cosecant squared of the blob. All right, now notice how important the parentheses are. Without the parentheses, it looks like dot negative. And guess what dot negative usually turns into? Subtraction, all right? And then times the innermost blob. There's the last link in the chain, the derivative of the polynomial, 10x plus 2, close parentheses, okay? Notice how each factor, each link gets successively smaller. And that's how it should look, right? And you're done. 3 layers, purple, red, green, 3 factors, purple, red, green. If you clean this up now, there's some minimal stuff you could do, right? You could bring the negative out front with the 3. You can maybe bring the 10x plus 2 factor in the front. You could distribute the negative 3 to the linear factor. Whatever. I'm not going to mess around with cleaning it up. We'll just stop right there. Okay. If you could take the derivative, you can clean it up, especially if your parentheses are in place. This becomes a much different problem when you're lax, right? Let's say these red parentheses aren't there. That just looks bad, right? You kind of have that cosecant factor just suspended out there, and that can turn into subtraction instead of multiplication. And look at this. This is even more dire. Watch this. If at the very end, where mistakes usually are made, you don't do parentheses, is that the same now? No. That's like all of that blah, 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 blah times 10x, pause, and then plus 2 at the end, right? That's not right. So be careful, be deliberate, do it right the first time. Yes, sir. High five. I think it's worth it. Yes, sir, Mason.
For the quiz, are we gonna have to clean up something?
No. For the quiz, I'm not going to give you something this ugly and expect you to clean it up. Okay. If I expect you to clean it up for the quiz, it'll be something simpler. This is just like, do you know the derivative stuff? We'll save the algebra for the big game, for the final show. Yeah. It'll be chain rule and maybe particle motion. Yeah. Like something like this. And then maybe a particle motion question, or maybe a particle motion equation
That's chain.
that requires chain rule. Take the derivative, right? Okay, that would be super lit, right? Okay. Any comments or questions on the chain rule so far? All right. Well, let's move on to example 2. Find all the values of this function for which the derivative is 0 and for which the derivative doesn't exist. This is going to be a pretty common thing for us to do on our own once we get to chapter 3 without any instruction to do so. A lot of the times we're taking the derivative and we're setting it equal to 0. Why is that an important number? What type of slope has a 0? What type of line? Horizontal line, yeah. And those horizontal tangent lines are going to give us the possible locations of local max and mins, right? It would look something like, here's one, something like that. Notice right here, and right here, we have tangent lines that are horizontal, 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 horizontal. And of those 3 x values, notice 2 of them are local extrema, local max, local min. The other one, the first one, is not, but it's a potential place. So finding those values that help us maximize or minimize quantity is very important. Now, for which the derivative doesn't exist, there's going to be a lot of values if it's not in the domain, but mainly we're looking for something like this, like that, or like that, right? Now, these first and last don't exist because they're sharp turns. The middle one doesn't exist because the slope is what? It doesn't, it's vertical, it's infinity, right? Now, notice that 2 of these are actually local extrema. We have a local max and a local min. So where the derivative fails to exist can also possibly be the location of a local max or min. Okay, that's why we do that. So anyway, it says to find all values. First thing we want to do is let's think about the domain of f. Okay, because wherever the function is defined, the graph is going to exist. Wherever the function is not defined, not only will the graph not exist, but neither will the derivative, right? So what's the domain? Well, when we're doing domain of single defined equations like this that aren't piecewise, we're trying to avoid division by 0. Do we have any denominators in this equation with a variable in it? No, they could be in disguise though, right? You can have like a negative exponent with a variable, but I don't see that either. Okay. The other thing we're trying to avoid is square roots or 4th roots or even roots of a negative number. So do we have any square roots or 4th roots with a variable underneath it? I see a root, but it's a cube root. Can we have negatives under a cube root? Yeah, we certainly can. But oh, look, we're not even going to here because it's squared. So unless it has a natural log or log in it, we're good. It passes those 2 hurdles, right? Guess what the domain is? All real numbers. That's cool. All right. Now, to take the derivative of this, we need to, we need to get rid of the radical, don't we? So just as if it were the same as like the cube root of x, we would write that as x to the 1/3, yes? So we could use the power rule. It's the same thing here. So we're going to have f of x equals x squared minus 1 squared, and then all of that to the 1/3 power. Now, if we leave it like that, we'll be successful, but how many layers do we have there? The way it's written. We have 3 layers, right? Blob to the 1/3, blob squared, and then the blob, x squared minus 1. Can we help ourselves by eliminating one of the layers? Yeah, simplify early and often. We can combine these 2 right here. Some of y'all have already reflexively done that. That's great. That's x squared minus 1 then to the 2/3 power. And now we can't distribute that, right? We can't expand that. So that's as good as it gets. But that's good. There's only 2 layers now. So let's take the derivative. I'll use a different flavor here. Blueberry. Oh, that reminds me of a good joke. Joe, what's a ghost's favorite fruit? Boo, berries. Hey, Here's a great Halloween joke. And it deals with tomorrow's twin day, right?
Yes.
Why is it hard to go trick or treating with twin witches? Because you won't know which witch is which.
Wow.
Which witch is which? Twin witches. All right. Blob to the 2/3. Here we go. F prime on the left. Multiply and subtract. Multiply and subtract. Look how I do that. I leave the blank wide open. And then I come back and put the blob. Do you have to do it that way? No. But here's what I've come to notice. And it's not just me, because I'm the master of careless mistakes. Here's what I've seen students do. Okay, it's a chain rule. So I'm going to multiply. So 2/3 times, and then it's the quantity. That's x squared, and then -1. And then I close the parentheses. Okay. And then times the derivative of the next layer, which is the derivative of x squared. That's 2x. Yeah. Go gadget me. What did I do there? What did I not do there? I forgot the exponent, right? I see that a lot because it's like a different train of thought. You're doing the chain rule in your head, and then this is just transcribing. This is just rewriting what's up above. So your brain kind of switches modes and it's detail oriented, trying to make sure everything. And then by the time you get to the end, even though it's a short distance, some people forget to put the exponent. Now, if that's not you, then do it how you want. But guess what I tend to do sometimes? Forget the exponent. So I'm going to put -1/3 and then leave it blank. Now, if I do that, how likely am I then, when I do the chain rule on the next layer, how likely am I to leave that alone and walk away and say that's the answer? Not very, because there's obviously something missing, right? Obviously. So that's x squared -1. But if you forgot the exponent, is it obvious that something's missing? No. If you've detached from it mentally, when you come back and look at it, you're not necessarily going to notice it. Is that B lunch already? Oh, that's it. Oh, advisory's over. That's just me keeping the desk from floating away. I don't know. That was weird. The lunch advisory's over, and I just felt compelled to do that. I have no idea why. Yeah. Okay. -1/3. All right. Got it. So there's the derivative, right? Multiply, subtract. Blob goes in there, and then times the derivative of the blob. More than one term. Yeah. Yeah. Or if there's another layer. Now, I'm going to have them. I didn't put them there because I was pretending like I was a careless student. But when I do it myself, I put them there. I always have the receptacles around them. Protection. Okay. And now we clean it up. So if we clean it up, this is really all over 1. You're going to have a denominator. What's in the numerator? You have a 2 and a dos equis, which makes 4 equis, right? And then what's in the bottom? The factor of 3. And then the other thing comes to the bottom and goes back under the cube root. Come on, show up, baby, show up. There it is. This is what we do in pre-cal. This is why we spend so much time with exponents, so that you can go straight from the derivative to this answer. Is everyone okay with it? I highlighted to try and show where things come from. That's really 2x over 1. Yeah. So this is your cleaned up version of f prime. If we're going to use f prime, we want to clean it up first on the front end. Okay. Now, I might even bring f prime down here. There we go. There we go. Now, I'm going to use it twice. So the first thing I'm going to do is I'm going to set it equal to 0. And you always, always, always have to show the equation you're solving. This would suffice. F prime of x equals 0. Guess what? Very often on a free response, that's enough to earn a check. Now, when I set the name of the function equal to 0, that's great. That's one thing. But since I have the expression that it's equal to on the right, you could also do that. I'll say and or, right? Some people like to be thorough. So you could also say 4x over 3 cube root of x squared -1 equals 0. Either way, you don't get a bonus check for that. Those are both equal to f prime. Now, when I set the actual expression equal to 0, that's something I can work with algebraically. Bless you. Do we want to solve this equation now by multiplying both sides by the denominator? Good. No, but that's how they teach you in algebra 2. We just had that discussion in pre-cal. You don't want to do that because when you do that, you lose variable information from the equation. And in general, when you lose variable information from an equation, you lose solutions, right? So we don't want to do that. Here's how we're going to arrive at the exact same thing, though. A fraction is equal to 0 when the numerator alone is 0. That's how we get there. We still have this entire function fully intact, but we know that a single fraction, is going to equate to 0 only when the numerator is 0. That's it. Okay. So do we have to write when? Kind of, yeah. If it's not there, do you lose points? No, but it's just merciful grading because this is by a consequence of a theorem, right? All right. And now we solve this and we divide through by 4, which is fine. We get x equals 0. So what do we know? We know at x equals 0, this function has a horizontal tangent. If I can spell it, horizontal, there we go. Because the derivative there is 0. So it's going to be one of 4 things. It's going to either be this, or this, or this, or this. Right? X equals 0, x equals 0, x equals 0, x equals 0. It's going to be one of those 4 things. Those all have horizontal tangent lines. See that? We don't know which one it is. In chapter 3, we're going to learn how to figure it out pretty easily. We can actually use the derivative to tell us which one it is, right? Preview of coming attractions. If I look at the sign of the derivative immediately to the left and right, that should be enough, right? Because notice in the first one, it's increasing on both sides. So the derivative should be positive on both sides. And this one, when it's decreasing, the derivative should be negative immediately to the left and right. Now over here, when it's a local max, it goes from increasing to decreasing. So that's where the derivative should change from negative to positive, okay? Anyway, that's later on. So right now, we just know it's one of those. All right, now we also want to know where it's undefined. So we're going to say f prime of x equals dne, okay? Because that's kind of what it said. Now, again, if you want, you could say 4x over 3 cube root of x squared minus 1 equals dne. Either one of those. Or and. When you do and or on the slash right there, that means either one of them, right? And when you write it, you can either do and or and you could do or and or. It's kind of funny. Now, it's a single fraction again. You're going to be striving to get single fractions on your derivatives or even second derivatives all year long because they make it so easy to answer these 2 questions. Where is it 0? When the numerator alone is 0. When is it undefined? When is the single fraction undefined? When the denominator is 0, right? Can't divide by 0. So that's going to be when 3 cube root of x squared minus 1 equals 0. Okay. So I still have the full equation intact up above, but now I know I can't divide by 0. So let's set it equal to 0 and solve. Oh boy, this is a fun one. Should I cube both sides first? Because I think some pre-cal kids might mess that up. You certainly could, but then you'd have to cube both factors. Can we divide through by 3? Yeah, because 3 is not a variable, right? It's a constant. So you can get rid of constants. If you divide through by 3, it's gone. And now you can cube both sides. 0 cubed is 0. That's cool. And now from here, you can either solve by factoring, right? It's the difference of 2 perfect squares. So it factors into the product of 2 whatchugets? Conjugates, that's right. Or you can extract the square roots, which is what some of y'all are doing. That's fine. X squared equals positive 1. So when you take the square root, you get x equals what? Very good. It's a little bit more dangerous to do it this way because some students, again, in haste, forget to take both plus and minus roots. If you factored it as x minus 1, x plus 1, the roots are a little bit more obvious, right? Because you see two factors. So don't forget plus or minus when you take an even root. Now, are those in the domain of our function? Yeah, because we said in the beginning the domain was all real numbers. So let's see, those guys at 1 or -1, we're going to have this, or this, or this, or this, right? When you plug in a 1 or a -1, you get non-zero over 0. And remember, non-zero over 0 means undefined because it's some type of infinity. So those are the 4 ways you can get infinite slopes. All right. One of them, I'm sorry, 2 of them are local extrema, local max and mins. All right. That's all it asks us to do. We're not really going to get into making the number line chart, but I don't want to walk away just yet. Do you? I'm kind of curious what they look like. So let's go to the calculator. Calculator. And that's not the calculator. There's the calculator. Load the ROM. This is exciting. Like we've been doing this, like we've been flying the plane by instrumentation only, right? We haven't been able to see out the window. And we're good navigators. We can read the gauges, but now the clouds are clearing and we can actually see, right? Now, when I type that in to y equals, there is a cube root button, but I don't like using it. I'm actually going to type it in as x squared minus 1 to the 2/3. It's just a little bit faster. X squared minus 1 to the 2 divided by 3rd power. Double check, triple check. Let's hit zoom 6, standard viewing window. Ooh, yeah, nice. That's what it looks like. Nice. So let's go ahead and transfer that to our paper. Transfer that. Here is -1. There's 1. It looks like this.
It was kind of.
Well, it has y-axis symmetry. It's an even function. I know my hand got shaky. Old people, right? Oh, so I know it's about lunchtime, and this kind of makes you hungry for something, right?
Whataburger.
Right? What happened? Yo, what happened?
Put +1 at the end and make the Whataburger.
Supersize it? No, there it is. So that's what it looks like. So if you notice, at -1, there is a vertical tangent line. It's a sharp turn. And it is a local min. At 0, we do have a horizontal tangent line. And then at 1 again, we have another sharp turn. This function does have symmetry. When we get to chapter 3, that's one of the things we're going to be looking for, right? You could tell it's an even function simply because there's only one variable and it's squared. So plugging in a -x and plugging in a +x are going to give you the same output, y-axis symmetry. Okay. Whataburger, the best taste in town, Whataburger. That was our little jingle from like 1982.
Still stands.
Yeah, still does, right? The best taste. Yeah.
Best taste in town. Agreed.
Best taste in town, Whataburger. All right. You want to see how we could have done that without the graph? A little preview of coming attractions? Yes, I think y'all do. Yes, I think y'all do, right? Who wants to see it? Come on, everybody. All right, watch. We don't need no stinking calculator. Watch. We're going to get down to what I call in chapter 3, the full-fledged factored version of f prime, or the f prime, the f prime, the full-fledged factored version of f prime. That's it right there. Now, we're going to find these values that are in the domain of f that make it 0 or undefined. We call those values, whoa, ease off the orange there, dude. We call these values critical values, okay? Preview of coming attraction, critical values. Now, critical means important, right? But in this case, it is a vocabulary word. It's not just an adjective I threw in there. They are very important, but in calculus, they're known as critical values. Here's all we have to do. Let's come up here. We're going to make a little number line chart, X and then F prime. The line that divides the two rows is the number line. Let's put our critical values on there in order. Here's -1, here's 0, and here's 1. Uh-oh, I'm encroaching on the graph itself. Let me come down here. There we go. There's 1. Okay, now, here's the cool thing. If those are the only values where the sign of the slope can change, because they're the only ones where it's 0 undefined, I can choose a test value from anywhere in those intervals. And if I can figure out the sign of F prime, I'll know if it's increasing or decreasing. So pick a number to the left of -1. -2. Pick a number between -1 and 0. -0.5 and then 0.5 and then 2. Make it easy on yourself unless you like the challenge. Now, we're going to plug those in to this right here, into the FFFF prime. And we're going to look to see what the SIGN sign is, okay? If I plug in I need to get closer to it, right? When does close count? Slow dancing, hand grenades, horseshoes, and the first derivative test. Slow dancing? Oh, yeah. Let's plug in a -2. I get a negative in the two. Oh, yeah, that's right. COVID. -2 over. And what do you get when you plug a -2 in the bottom? -2 squared is 4. You get positive, right? So a negative over positive is a negative. So that first interval is negative. That means F is decreasing everywhere to the left of -1. Is that true from what we see? Yep, it's decreasing. Now, plug in a -1/2. In the top, you're going to get a negative, but in the bottom, you're going to get +1/4 minus 1. That's -3/4. And the cube root of a negative number is a negative number. And what's a negative divided by a negative? Positive. So now from -1 to 0, it's going to be increasing. Plug in a +1/2 and you're going to get a positive over a negative, which is negative. So now from 0 to 1, it's decreasing. And then finally to the right of 1, I'm going to choose 2. I get a positive in the top, positive in the bottom. That's positive. And there you go. And now here's the beauty of the test. Not only do we know where this graph is increasing or decreasing, because we know the sign of the derivative on every interval, but look, when your derivative changes from negative to positive at a critical value, this one's vertical, it's going to be decreasing to increasing. We have ourselves a local min. And anytime the first derivative changes from positive to negative at a critical value, we're going to have ourselves, in this case, a local max, but it's a horizontal tangent, so it's a smooth turn. Hang in there, Ben Delay. And then anytime the derivative changes from negative to positive at a vertical tangent, you're going to have another local min. So you have a local min, local max, local min. Okay, so there you go. We're going to do that in chapter 3. And then when we get into it in chapter 3, we're going to be able to fly through it because there it is. That's the basic idea. So the derivative not only gives us the location, but it also gives us the tools to assess what's happening at the location just by analyzing the slopes. So this is a preview of coming attractions. Polka, right? And you know what? I just thought whenever I give you a preview of coming attractions, I should come up with a little dance, and we call it the polka dance, right? Hey, speaking of polka, it's about to be Worst Fest. I should have worn my Worst Fest hat. In fact, I think I will after. No. My kids are still in college, right? Right. Yeah. I don't know. Yeah. Oh, you mean like a Worst Fest Opa? No, I've never joined. They work too hard. They work too hard. Yeah. I know a lot of Opas. It's like owning a boat. It's always good to know someone who owns a boat. It's always good to know someone who's an Opa. Because then they give you the drink tickets and the food tickets and you don't have to do all the work. Right. Connections, people. All right. You know what? If I could go back and relive my life, I would do it again. I would do it again. But I would probably join the Wurstfest Association like 23 years ago. A lot of guys I went to school with are like really high up now. They're young like me, but they're like Brosa Opas.
That's a secret society.
Yeah, yeah. Anyway, what's that? Yeah, the Omas or the wives. All right, how much time do we have until the bell? 10 minutes. Okay. First of all, thank you everybody who's participating in Music Monday. I see some of y'all are out there doing Music Monday. I like that. Ethan's doing GPS Monday. That's another cool thing.
It used to be Metal Monday.
Oh, it was Metal Monday, but then we wanted to be more inclusive. Maiden Monday. Yeah, yeah, yeah. So I'm wearing a music shirt every Monday. This one is this is Eddie, and this is if you've ever seen High Plains Drifter with Clint Eastwood. He's dressed like Clint Eastwood in High Plains Drifter.
Why is there a possible?
Because it's his sidekick, like a Disney movie, right? Yeah. Okay. All right, let's do example 3. Ready? If f of x is equal to this, find the domain of f. That's the natural thing that we would do anyway if we were faced with a function. We're trying to avoid division by 0, and we're trying to avoid square roots of negatives. Do we have any radicals in this problem or hidden ones with fractional exponents? No, but we do have a denominator, don't we? With a variable. So for what value of x is 1 minus 2x cubed 0? Yeah, you can go off to the side and say, hey, 1 minus 2x cubed, this is what we did in pre-cal, can't be 0. And then you take the cube root of both sides. Okay, and then you add 2 to both sides. This is just algebra 1, right? And you say x cannot equal 1/2. Now you could probably just look at it, right? And know that, hey, 1 minus 2x can't be 0. And then you can solve that in your head. Whatever it takes, we're going to answer the question. Big D sub f, that's how you write it, colon not equals. Colon not equals. And you could say it's the set of all x's such that x ain't 1/2. Or you could say D sub f colon x epsilon. And this was a little more fun, right? Negative infinity to 1/2, and then you step over it like it's a cow patty. 1/2 to infinity. So notice they both define the variable x and then x epsilon for interval notation. Okay, either one of them. So here's what we know. The function doesn't exist at 1/2. Is it a whole or a vertical asymptote? It's a vertical asymptote. There's 2 ways you can tell. Did you say cancel? Divide out. 1 out, not 0 out. The 1 minus 2x factor, there's 3 of them. They don't divide out, so they're non-removable factors. Therefore, it's a non-removable. But here's the other way to do it, right? If you plug in a 1/2, you get non-zero over 0. Non-zero over 0, remember, is some type of infinity. And what exists graphically to force the y values to infinity or negative infinity? Vertical asymptote. Yeah, that's okay. All right. Now, the follow-up question. Does the derivative exist at 1/2? It sure don't. If the function don't exist, then how can the derivative exist? Because we're talking about the slope of the tangent line of the graph at that point. And if there is no point, what's the point?
There is none.
There ain't no point. What's the point? You don't know which is which. All right. Part B. Part B. Show that the slope, we have to what, 1235? Okay, show that the slope of every single line that's tangent to the curve, show that it's positive. Show that it's positive. What would you do? Let's see. Show that the slope of every tangent line at every point. What do we call the machinery that allows us to find the slope of the tangent line at every point? Starts with big D, the derivative. Yeah. Do we have the derivative yet? No, we don't. So we need the derivative. So let's bring down the function f of x equals 1 over 1 minus 2x cubed. Now, if we have it like this, we certainly can use the Hody-High rule. It's a quotient. But recall what I told you on Friday. Whenever you have a quotient like this, and the numerator is a constant, it's faster and easier to what? Bring it up to the top. Man, that's awesome, Mason. Mason is on fire. He is lit today. And then the 1 kind of disappears because it's an implied factor. That's extra nice. So now we're going to use the chain rule. We were going to have to use the chain rule anyway inside the Hody-High rule, but now it's just a chain rule. So how many layers do we have? 2. So 2 layers. The outside layer is blob to the -3rd, and then the inside layer is blue. So here we go. On the left, we get f prime of x. Don't forget that part. Multiply and subtract. -3 quantity to the what? -4. Thank you. And again, notice how I did it. Feel free to adopt my style. Not the way I dress or anything, but my math style, right? Oh, man. I get dressed by myself now, and so I feel like a big boy. My wife is gone. My daughter's gone.
Why's your wife gone? Where's your wife? And now these
I mean,
three-
she's just left me every morning at 6 o'clock. She leaves to go to work, and I miss her, but she comes back. And then she's like, "Did you wear that to school?" And I'm like, "Yes." Right? I have to change. If I beat her home, I have to change real quick. Yeah, change back in like normal clothes. Anyway, I'm not done with this, am I? That's just the outer layer. Times the derivative of the next layer. 0 minus 2. I always put the next layer in parentheses, even if it's just one term, but especially if it's negative in the front, because you know what I hate? I hate dot negative. I hate dot negative. If I see dot negative, I'm going to go ahead and pull what Papa Bear did when he came home and saw that Goldilocks had eaten their porridge, sat in their chairs, broken their beds, watched their DVDs, ate all the Pringles, whatever. I'm going to go, "Grr." I think that's what he did. And then Goldilocks ran away. Yeah. I'm going to get angry. Okay. So don't do dot negative. Now, if this were just a quiz where we're taking the derivative, we can walk away right here. But we want to use this dude. So guess what we're going to do? We're going to clean him up. Clean him up. All right. So you can think of all this over 1 if you want. In the numerator, we're going to have a -3 times a -2. That's a +6. And in the denominator, we're going to have a 1 minus 2x to the 4th. And notice it's still equal to f prime. Beautimus. Now, go back to the question because I forget it did what it was asking. It says, show that the slope is always positive. So I can rewrite that to show that the derivative is always positive. Well, let's see. For any value of x in the domain, which is everything except the half, what is the numerator going to be? Positive. I thought you were going to say 6. I was ready to come back with what kind of 6? And then you were going to say a blue 6. And I'm like, you smart cookie. It is positive. And then notice any value in the denominator except 1/2 is going to be raised to the 4th power, which is going to make it also what? Positive. What's a positive divided by a positive? Positive. So how do we show that? How do we show that's positive? Do we show that's like it's smiling, like it's happy? That looks like a weird cyclops, doesn't it? But he's happy. That's not how we show it's positive. You know how we show it's positive? We just say this is greater than 0. Right. For all x, what? For all x? This is where you can lose it, except 1/2. That's so important. That little tail end piece can cost you a whole check. And this part might only be worth 1 check. So you have the insight, but you didn't implement it. Okay. That's all you have to do. You're finding the derivative, you're cleaning it up, and you're saying it's greater than 0 for all x in the domain. Now, here's what else is cool. Remember that 1/2 was not in the domain of the function, so the function doesn't exist. I asked you, does the derivative exist at 1/2? And y'all all said, heck no, it can't exist, right? Does the derivative function know that it's not supposed to exist at 1/2? Yes, it has a built-in safeguard. If you try plugging in a 1/2 into the derivative, it's going to be like infinity, right? It'll be 6/0, non-zero or 0. It'll tell you the slope is infinite. So, or it's approaching infinity, right? Because there's a vertical asymptote there. And if there's a vertical asymptote, what are the slopes approaching? Yeah, as the y values approach infinity, so are the slopes. But as y goes to negative infinity, the slopes are still getting vertical, okay? Is that all it asks us to do? We're done with that one? Okay, so we're taking baby steps, right? We're using the chain rule. I'm kind of hungry now, aren't you? Yeah, lit Air Force, right? Lit Air Force. This is how the pilots in the Air Force know where to fly, because they have lights on the front of their airplanes. And so they, "Ooh, look out, birds, here I come." And they're lit, the lit Air Force. They do watch out for light and for feet that stick out. All right. Y'all have a great lunch. Thank you for allowing me to teach during advisory. I will continue to do that until y'all rebel. Have a good